My name is Qifeng Li. I'm an assistant professor affiliated with the Department of Electrical and Computer Engineering at CECS. I'm also affiliated with the faculty cluster of Resilient, Intelligent, and Sustainable Energy System. Before I continue to my presentation, I would like to thank the seminar committee as well as Dean Giorgio Paulos for giving me this opportunity to introduce myself as well as my research here. So first, I would like to give a little bit background about myself. I obtained my Ph.D. degree in electrical engineering from Arizona State University in 2016. And I joined UCF in 2018. Before I joined UCF, I was postdoctoral associate with the Department of Mechanical Engineering at Massachusetts Institute of Technology. After I joined UCF, my teaching is basically about power system. Currently, I have 4 PhD students working in my group with 2 undergraduate students and 1 visiting scholars. For the past 2 years, my research funding mainly comes from NSF and the Department of Energy. In the past 5 years, my research is basically focused on applying theoretical tools like nonlinear system theories, machine learning, and various types of optimization technologies like convex optimization and multi-objective optimization to improve the efficiency, intelligence, and resilience of multi-energy systems. So what is multi-energy systems? Here I provide a big picture of the multi-energy systems. By its name, we can know that multi-energy system means a system that consists of multiple energy networks. For example, the electric power network, the heating or cooling network, and gas network. And those networks connect with each other at some points. For example, the combined heat and power generation plant. In addition to the 3 types of energy network, a multi-energy system also consists of a lot of system components like solar generation, wind generation, energy storage, as well as the demand side. For example, the customer, electric vehicle, something like that. And moreover, for solar, there are 2 types of solar generation. First is to convert the solar into electricity, and convert the other type is convert the solar into heat. So this is the big picture of multi-energy system. One more thing that I'd like to highlight for the MES is that recent years we find that MES has stronger interaction with other critical facilities like the transportation system and water distribution system. Take the transportation system, for example. We know that currently the number of electric vehicles is growing very fast. So it provides a new point of contact from between the transportation and the multi-energy systems. For example, when we decide the place for the charge station for the electric vehicle, we need to consider both the transportation network as well as the power grid. So for the connection with water distribution system, I will give you a further example in my later presentation. Actually, I attend many of the previous seminars. I realized that some of our colleagues also work on optimization of complex network system. That's not surprise because optimization it's necessary technology in almost every domains. For example, machine learning is mainly based on optimization. But my point of focus is a little bit different, because for a complex network like multi-energy system, there are mathematical model for almost all system components are nonlinear, and so that non-convex. When we build up an optimization model for the multi-energy system, it is hard to get rid of the non-convexity. What does non-convexity mean? So let me use this quick example to give you the basic idea. For such a simple example, if you plot the feasible set onto the XY domain, then the feasible set looks like the flower shape. So here, the flower looks beautiful, but when you do this for a big system, then this is a nightmare for computer. So the idea of convex optimization is to relax or approximate the non-convex feasible set into a convex one, so that the problem can be easier to solve. That's very important for multi-energy system, because for some optimization problem in multi-energy system, it is very important to have the problem very easy to solve. So in the past 5 years, we have developed this for the power network as well as the fluid network. The convexification need to do case by case. So this is the point that I'd like to emphasize. In what follows, I'm going to quickly introduce 3 ongoing projects of my group. The first one is funded by NSF. Our collaborator is from MIT. In this project, we focus on the stability and efficiency of microgrid. So the high-level idea is to do the optimal trade-off between the stability and efficiency. So the technical contribution for this project is to combine the electrical stability theory and convex optimization. As we know, microgrid is the platform that people integrate the renewable energy to improve the efficiency and stability that help us achieve a sustainable future. So this is the impact of this project, and through this project, we support the research of 1 PhD student and 2 undergraduate students. The second project is about the post-disaster restoration of power system after disaster. This project is sponsored by Department of Energy. Our collaborator is from Pacific Northwest National Lab and Dominion Energy, which is the utility of Virginia. So people has been studying restoration for years. In this project, we include some new elements like the coordination of the three part of the modern power system: the transmission system, the high voltage transmission system, the low voltage distribution system, and the communication system. And we also introduced some new technologies, for example, the mobile energy resources, as well as repair cool. So this is a very complicated problem in terms of optimization, and the contribution from the UCF side is to develop computational efficiency approach to solve such a very complicated optimization problem. After disaster, we are trying to restore the power supply as soon as possible. So it is very desirable to solve the optimization problem timely. So the last project is about the water energy nexus, which is a new engineering problem. In this project, the basic idea is to co-optimize the water and power system. The very basic idea is to move the energy that consumed by the water system to to the period that other electric customer is not that many. For example, during night, we turn on the pump to store water in the tank, or to turn on the desalination plant to consume electricity, and try to avoid use electricity during the periods a lot of people are using electricity. The idea is pretty straightforward, but the problem is how to realize this goal through optimization and control. So this is what my previous research for the future. I'm going to continue for near term. I'm going to continue my current research and current collaborator. For long term perspective, I'm going to go deeper into a new research domain called learning aid optimization. Machine learning, it's about optimization, but the idea of learning aid optimization is a little bit different. We're trying to use machine learning to help us improve the efficiency of optimization when we use the optimization theory to solve complex optimization in complex network system like MES. So I will broaden the collaboration out inside and outside UCF in the future. So I'd like to close my presentation by thank my supervisors at UCF and my former supervisors, the member of my research group, my collaborator and sponsor. Thank you.